Lipids are our first class of biomolecules that we are discussing in this course. The property that all of the lipids have uh, is that they're not soluble in water. So that seems kind of like a broad principle, but that is really one thing that all lipids have in common. All of them are insoluble in water, which would mean that they'd be soluble in organic solvents. If you look at the structure of some of these lipids over here, notice how many carbon-hydrogen bonds they have. All these carbon-hydrogen bonds, some of them have polar ends, like the carboxylic acid group. Some of them have esters, which are slightly less polar, but note all of them have a lot of carbon-hydrogen bonds here, and these are all non-polar. The intermolecular force responsible for these is the London dispersion or van der Waals forces, makes these non-polar overall, so they are not soluble in water. Lipids are classified in four main groups. We have triacylglycerols, waxes, phospholipids, and fatty acids. Sorry, not fatty acids, steroids. Triacylglycerols, sometimes these are called tags. Triacylglycerols. Most lipids are what's called amphipathic. Amphipathic means that part of the molecule is hydrophobic, water-fearing, and part of the molecule is water-loving, hydrophilic. So if we have um, a fatty acid that looks something like this, and we have a big carbon chain, this would be the hydrophobic part, and this is the hydrophilic or water-loving. Why is it water-loving? It's because it's a carboxylic acid. We know that carboxylic acids are soluble in water. They're very polar. They can also hydrogen bond. Lipids can be classified as hydrolyzable, which means we can hydrolyze them, or non-hydrolyzable. So they're either saponifiable or they aren't. So if we don't have an ester or an amide or a phosphate, they are non-hydrolyzable. The hydrolyzable lipids are the triacylglycerols or the tags. We can hydrolyze waxes. We can hydrolyze phospholipids and sphingolipids. The non-hydrolyzable ones, the big category here is the steroids. The main function of lipids is energy storage. Again, main function is energy storage, but lipids also have a really important role in membranes. Lipids also do other things in the body, so emulsification lipids. These help fats move along with watery things like bile acids, so those help dissolve fats. And some of them are chemical messengers, like the steroids. So we have steroids like testosterone, estrogen, cortisol. Those are all important chemical messengers. And then there are also fat-soluble vitamins, but the main lipid function is energy storage. We'll start with fatty acids. Fatty acids are long carbon chains that have a carboxylic acid on one end. Notice we're going to have an even number here of carbon atoms. So natural fatty acids will have an even number of carbon atoms, and then a carboxylic acid on the end. These are generally going to be unbranched, and again, even number of carbon atoms. So a lot of times we'll just sort of have uh, a zigzag, be represented as like a zigzag, bunch of carbon atoms, and then a carboxylic acid on one end. Fatty acids can either be saturated, so that would be all single bonds, or unsaturated. The formulas for fatty acids can be shown as line bond formulas, but a lot of times you will see this condensed structural formula where the number of carbon atoms in the center just has a subscript telling you how many there are. That's just to make it so that we don't have to draw these humongous molecules. Fatty acids overall are considered nonpolar. They have a long hydrocarbon chain. They have the polar carboxyl end. And just like with all of our other molecules, the melting point increases as the number of carbons increase. That's because the molecular mass increases. There are more carbon-hydrogen bonds to interact with the other carbon-hydrogen bonds. And the main intermolecular force here is the London dispersion or the van der Waals. Now, the melting point is going to decrease as the number of double bonds increases. So if we have only single bonds, the melting point is going to be much higher than if we have some double bonds. But if we have multiple double bonds, we have multiple degrees of unsaturation, then the melting point is going to decrease even more. So our saturated and trans unsaturated fatty acids are going to be solids. The cis unsaturated are going to be liquids. So the saturated and trans unsaturated, these are typically called fats, and the cis are called oils. Saturated fatty acids, again, they have only carbon-carbon single bonds and then a carboxylic acid on the end. They have very neat stacking that can happen. So we have sort of this chevron pattern down here. And saturated fat is often found in meat products. So, this white part on the steak, this is tallow. This is stearic acid. So it's a solid at room temperature. Of course, you probably know that if you cook it and heat it up enough, it will kind of melt and get softer. Here's some saturated fats that you have probably heard of. Again, stearic acid, this is animal fat. This is that white in the steak. Another saturated fat is palm oil, so palm. And then that's palmitic acid. Then we also have lauric acid. That's nutmeg. Nutmeg is not very common, but coconut oil is something that a lot of people use in cooking, right? So coconut oil, that has 12 carbon atoms, and you probably know if you have coconut oil at your home, at some points in the year it might be a liquid, and at some points of the year it might be a solid. That's because its melting point is relatively low. It only has 12 carbons versus stearic acid that has 18 carbons. So the melting point of coconut oil is 43 degrees Celsius, a little bit more than body temp, and animal fat is 69. So it's going to be higher because there's more carbon atoms there. These are all, again, saturated fats. They all have single carbon-carbon bonds. Our unsaturated fats are going to have at least one double bond, and that double bond is going to be a cis double bond. In all natural oils, the double bond is a cis double bond, and that causes these molecules to have these kinks that reduces their melting point so that they are liquids at room temperature. These are typically going to come from vegetable sources, vegetable oil, olive oil, grapeseed oil. Here's some examples of polyunsaturated fatty acids. So some of these, linoleic acid with 18 carbons comes from soybeans and sunflowers. We also have linolenic acid from corn. Arachidonic acid is going to come from meat, eggs, and fish. Arachidonic acid, notice it is polyunsaturated. We have 1, 2, 3, and 4 double bonds. Linolenic acid has 1, 2, and 3 double bonds. Linoleic acid has 2 double bonds. The more double bonds the molecule has, the lower the melting point is going to be. So notice arachidonic acid is a -50 versus linoleic acid, which is a -9. You might be asking me, well, what is going on here? Because you just told me that the saturated fats are found in animal products. There's also arachidonic acid and other fatty acids, but they're in animals. There is a lot of that stearic acid, which would be like the hard fat. Those unsaturated oils, they cause kinks in chains, and so it makes it so they can't stack neatly on top of one another, and it results in lower melting points, most of them are going to be liquids at room temperature. Here's some more examples. So the stearic acid, again, that was saturated versus these mono and polyunsaturated. This is just sort of all in one table here. The oleic acid, this is from olive oil. This is an example of a monounsaturated oil. It has a melting point of 13 degrees Celsius, and so it's a liquid at room temp. If you put your olive oil in a refrigerator, sometimes it kind of becomes like a semi-solid. That's because its melting point isn't super low, it's 13. We can create fat in our bodies. So we can create fatty acids in our bodies from a process called lipogenesis. We're not going to talk about this all that much in this class, but your body can produce fat just like animals produce fat. And you can also get fats through the diet. Now, most fats are actually called non-essential because that means that your body can produce them. But there's a special type of fat called essential fats. There'll also be essential amino acids when we get to that chapter. Essential means that your body cannot produce it. You need to get it from your diet. Here's just sort of a summary here. Fatty acids, non-essential are saturated and monounsaturated. And fatty acids that are essential means that you must get them from your diet, are going to include the omega-6 and the omega-3 fatty acids. So the linoleic acid and the arachidonic acid. The omega-3 get a lot of bonus points for being good for the brain, good for your cardiovascular health, and typically here they're talking about the EPA and DHA. When we're talking about the essential fatty acids and omega-6 versus omega-3, the omega-6 or 3, what it refers to is where the double bond is starting from the end of the chain. So we have our carboxyl end, and I recognize when you're naming, typically you would call that carbon number 1. But for the omega-6 and omega-3, what we're looking at is where that first double bond occurs from the end of the chain. So in the omega-6 fatty acids, that cis double bond, that first cis double bond is occurring at carbon number 6. In omega-3 fatty acids, that first double bond is happening at carbon number 3. So DHA is 22 carbons and EPA is 20 carbons. EPA is often the one that people talk about being really good for you. That's found in like salmon. So if you're getting fish oil, it's probably coming from fish. Fish that live in cold waters need a lot of cis double bonds so that they don't freeze when they're in the freezing cold water. They need something that has melting points that are really low so their bodies don't freeze. Here's our DHA again, another fatty acid, omega-3 with the first double bond starting at the third carbon from the end. Omega-6 are necessary for growth and development, but too much can cause inflammation. So if we have too much arachidonic acid, that can cause inflammation. And too much omega-6 can lower HDL. HDL is actually the good cholesterol, so you don't want to have too much omega-6. Omega-3 can kind of like thin out your blood. So it interferes with clotting, platelet adhesion, reduces chances of stroke. That's like all good stuff. But if you have too much of it, then it can interfere with clotting, and your blood can almost be like too thin. So you want to have a balanced ratio of omega-6 to omega-3s. You want to have like 1 to 4 omega-6 per omega-3s. So here's a question. Can a person survive on a completely fat-free diet? Again, you want to kind of pause here and think about this stuff. And the answer is no. A person cannot survive on a completely fat-free diet because These omega-3 and omega-6 are necessary. They're essential fatty acids that you must get from your diet. Draw the condensed structural formula for a fatty acid with 10 carbon atoms that is saturated, monounsaturated, and monounsaturated number 6. So what we'll do here is we'll draw first the carboxylic acid end. This is carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This would be my, let me move this over so you can see this a little better. This would be my saturated 10 carbon chain. It says draw the condensed structural formula. So again, I can kind of abbreviate by doing this. I have 1, 2, 3, 4, 5, 6, 7, 8, and then I have a CH3 on the end. If I have a monounsaturated omega-3, oftentimes I find it's easiest to draw the double bond first. So I'm going to draw the line bond formula where I just draw a double bond first. So this would be carbon 3, this would be carbon 4 from the end. That would mean I'd need those, whoops, I think I drew too many more. There we go. So this would be number 1, 2, 3, 4, 5, 6, 7, 8, 9. And here is our chain of 10 with a double bond at carbon number 3. This would be an omega-3. Let me do that for the omega-6. That would mean the double bond starts at carbon number 6. Again, I find it easiest just to draw the cis double bond first. That would be 6, and that's 7. This is 5, 4, 3, 2, and 1. This is 8. There's my 9 and 10. I kind of ended up with this flipped upside down. So this would be C, this would be a monounsaturated with an omega-6 double bond. Here's another question. So fish oils contain triacylglycerols formed from the polyunsaturated fat, this long name. Label the hydrophobic and hydrophilic portions of the fatty acid. Again, pause. This is our hydrophilic. And all this stuff with our carbon and hydrogens, this is our hydrophobic. How does the melting point of this fatty acid compare to its all-trans isomer? Well, it's going to be much less. Cis double bonds result in lower melting points and boiling points than trans oils and fats because trans act like saturated. Would you expect this fatty acid to be a solid or liquid at room temperature? I would say, based on what I have already read on the previous slides, I would definitely think that this is going to be a liquid at room temperature. What type of an omega fatty acid is this? Well, let's see. Let's count from the end. This is a 1, 2, 3. This is an omega-3 fatty acid.